recording. And a couple of things. First of all, my bad. I said the wrong date for homework due in class last time, and then I put the correct date on the email. I am sorry. Homework is due next week, Monday, April 6th. Yes, next week, Monday, April 6th. So is it working okay? Give me a thumbs up, thumbs down. Is it working okay to email out the homework? Is that working? Yes, we're good. Okay, super, sorry. Let's see, that was thing number one. Thing number two, your homework is not graded yet because I took the weekend off of school. Dr. Abling told us to, so we did. I don't think anyone in the math department did a ton over the weekend. So I will get your homework back to you. Overall, the homework was fine in terms of being submitted. Just a couple of small things. If you can, please, if at all possible, please send me a PDF as opposed to a picture. I had problems printing some pictures. They wouldn't expand to the full size of the page, and that's hard. So if you could, please send me a PDF. That would be greatly appreciated. And then secondly, write a little darker than you usually do. I didn't have anybody in this class that it was like impossible to read, but I had one or two in cryptography that I had to say, can you please resend your homework? So just write a little bit darker and take a look when you convert it to a PDF to make sure that it's readable on my end. Did submitting it in groups work okay? Yes, that was all right. It seemed to work on my end. Okay. My plan for getting homework, well, first of all, I reset up your groups, so you should be able to submit homework in groups again for the rest of the semester in the groups that you are set up with. And it's set the same way, so you can upload multiple files, you can have different people upload different pieces, that's fine. So that should work. And the way I'm planning to give your homework back to you is grade it, go and scan it, and then email it back to you. So that's my plan. I'm gonna scan it back in. I thought I was gonna take pictures of it and use the Cam Scanner app, and I started doing that for foundations, and I got like 3 pictures in, and I'm like, nope, done. We are going into WLC to scan this because this is gonna take 4 stinking ever, and I'm not doing that. So that's the plan for getting your homework back to you. My goal is to hopefully get it graded this afternoon or tomorrow morning and get it back to you sometime then. But I'll be honest, I don't care all that much about getting this homework back to you in a timely fashion because we're not doing stuff with series. So I'll get it back to you, I promise. It's just lower on my list than it usually is for other stuff. Okay, those were my announcements. What else you got? Anything else for questions? Homework questions, we can do those if you have any on section 4.1 or procedural questions in general on the course stuff. Anybody, anything with questions before we get into 4.2? We're going with no good. Okay, last thing, is it working okay for homework partners? Are you doing okay? Yes, no, maybe. Homework partners, you know who you're paired up with, that's working okay. Yes, we're getting a yes. Okay, awesome, thank you. All right, let's get into section 4.2 then. So let me share my whiteboard with you. Here we go. And section 4.2. Again, I can't see you, so if you have a hand raised, make sure to do it virtually, please. That's the one problem with the bigger class. All right, so section 4.2 is going to be transformation of initial value problems. Transformation of initial value problems. I'm getting way better at writing on this tablet, by the way. I wish I weren't, but I am. So here's the plan for today. We're going to talk about why we actually care about Laplace transforms. We didn't talk about why we cared about them previously. We are going to talk about why we care about them today. My recommendation would be to have the table of Laplace transforms somewhere that you can access during class, whether that's in front of you from your book, whether it's from Moodle on the computer screen, whatever it is. We're going to be using this an awful lot during class. So here's where we're at. If we are given a differential equation, so it's going to be a x double prime of t plus b x prime of t plus c x of t equals f of t. So my independent variable is t and my dependent variable is x. All right, independent variable is t, dependent variable is x. So ax double prime plus bx prime plus cx equals f of t. And we're going to say that this is initial value problem. So x of 0 is going to be x naught, and x prime of 0 is going to be x naught prime. So it's an initial value problem. We need to make sure to have initial values with this type of problem. And that's why the title of the section is Transformation of Initial Value Problems. Convenient. What we are going to do to solve this is apply a Laplace transform. And we're going to apply a Laplace transform to both sides of the equation. So that seems like I'm just introducing some weird level of extra steps and randomness because we've been solving differential equations for a while without doing Laplace transforms. Here's why it's going to be really, really handy. So just hold on to that for a second thought. Apply a Laplace transform to both sides of the equation to get an equation with capital X of S. So we're going to apply a Laplace transform to both sides of the equation to get an equation with capital X of S. Remember that the Laplace transform of little x of t is capital X of S, right? So this capital X of S is the Laplace transform of little x of t. That's where this is coming from. That still doesn't sound very good because now we've got this new function, capital X of S, that I still don't know what to do with. But if we do that, we are then going to solve for capital X of S, and that's just algebra. So we're going to solve for capital X of S algebraically. All right. Apply a Laplace transform to both sides of the equation to get an equation with capital X of S. We're going to solve for capital X of S algebraically, and then we are going to apply an inverse Laplace transform to get little x of t. So we're going to apply an inverse Laplace transform to get little x of t. 3 steps in this process, and we will do a bunch of examples and we'll work through them. Apply a Laplace transform to both sides of the equation to get an equation with capital X of S. Use algebra to solve for capital X of S, and then apply an inverse Laplace transform to get little x of t. And remember that little x of t is the solution to the differential equation. So that's what we were trying to find in the first place. Little x of t is the solution to the differential equation. That's what we were trying to find in the first place. If we were doing this for real in class, I would have you turn to the person next to you and decide which step is the hardest, 1, 2, or 3. So if we were doing this for real in class, and you will find this as a theme as we go throughout the rest of the semester, if we were doing this for real in class, I would have you figure out which is the hardest, 1, 2, or 3. Yeah, that doesn't work so well here, so I'm going to just give the punchline away. Step number 3 is the hard part. So this is the hard part. Sometimes you have functions where it's really easy to find an inverse Laplace transform. Sometimes it's not so easy to find an inverse Laplace transform. And so that is going to be the tricky part for this particular problem. The one other thing that we need to talk about is we've got this x prime of t and x double prime of t in our equations, right? we need to talk about how to do the Laplace transform of both of those. We know the Laplace transform of little x of t is capital X of s. That's no big deal. But we don't know the Laplace transform of the derivative and the second derivative. So turns out that the Laplace transform of x prime of t is s times the Laplace transform of x of t minus x of 0. That's the first one. Laplace transform of a derivative is s times the Laplace transform of the function minus x of 0. Or if we want to put that in shorthand, x capital X of s minus x naught. That's one that you're going to want to know. There's going to be 2 equations from today, maybe 3, that you're going to want to know. This is one of them. So the way that we do the Laplace transform of the derivative is s times the Laplace transform of the function minus x naught. Similarly, the Laplace transform of the second derivative, and the derivation of this is in my notes. You can walk through it if you want to and see where this actually comes from. This is going to be s squared, capital X of s, minus x naught times s minus x naught prime. S squared times capital X of s minus x naught times s minus x naught prime. So these are 2 of the 3 equations that you're going to want to know today. And I'll come back to the third one. Ooh, that is not a straight line. We'll come back to the third one in a little bit. But those are 2 of the equations that you're going to want to know, especially when you're doing your homework. Put those in the front of your notebook. Put them at the front of this section, wherever you want to do them. This is also why we can't do these type of problems if we don't have an initial value problem, because I need x naught and I need x naught prime in order to come up with these transforms. So if I don't have an initial value problem, I can't apply the method of Laplace transforms. All right, I'm going to stop sharing my screen for just a sec. I'm going to pause and see if we have any questions, and then we'll jump into some examples. So any questions up to that point? I can see you now, so you can do a real hand raise if you want to, or a virtual one. But any questions up to that point? I'll pop my screen share back up in just a second. Everybody good? It doesn't make much sense until we do an example, but everybody okay so far? Appears to be. All right, okay. Let's do some examples then. All right. The nice part about this Laplace transforms is that you don't have to worry what type of differential equation you have. You don't have to worry whether it's homogeneous or non-homogeneous, whether you have constant coefficients or not. That's not a big deal. So you have just one method for homogeneous and non-homogeneous equations. All right, let's work through a nice, easy one first. I say that, and then maybe it won't be easy. We'll see. All right, so x double prime minus x prime minus 6x equals 0. And I have that x naught is 2 and x naught prime is -1. X double prime minus x prime minus 6x equals 0. X naught is 2 and x naught prime is -1. So step number 1, Laplace transforms. I won't label these steps out every single time, but for this first example, I'm going to break them out so you can see where we are in the first part, in the point in the process. So Laplace transforms. Laplace transforms of the second derivative, s squared, capital X of s, minus 2s minus -1. Go back to that formula from the previous slide and make sure where you're understanding where all 3 of those parts are coming from. S squared, capital X of s, minus 2s minus -1. In the future, I will totally write it as +1, but this is the first example, so I want to show you where that's coming from. Okay, minus the quantity, s, capital X of s, minus 2. So this first part right here, the first 3 pieces, are the Laplace transform of x double prime. Second part right here is the Laplace transform of x prime, okay? And then we've got minus 6 capital X of s. I still got to do the right-hand side, but that's my left-hand side. All right. I'm going to expand so I can maybe see all of you. And I'm going to have you give me a thumbs up or thumbs down for whether that makes sense. Okay, yes, I can see all of you. Thumbs up, that makes sense. Do we see where the different parts of that equation are coming from? We got a thumbs up, everybody's good? Okay, thank you. Next part is going to be the Laplace transform of the right-hand side of the equation. This is where you'd want the table in the front part of your book. It turns out that Laplace transform of 0 is just equal to 0. And you can think about that if you have an integral with 0 in it, because remember Laplace transforms come from an integral. So if you have an integral with 0 in it, then you are just going to get 0 as your answer. So that's step number 1, Laplace transforms. Step number 2 is going to be solve for capital X of S. So I'm going to have to do some algebra. Do some algebra on your piece of paper. This is not differential equations. This is algebra. Do some algebra on your piece of paper. I will do some algebra on my whiteboard and we will see if they match. Hopefully they will match, but do some algebra. I'm going to unshare my white. No, I won't because I can't see it. Do some algebra and see if you can get X of S. I'm off by a negative with what I have in my piece of paper. Why am I off by a negative? Oh, that's why, because it's wrong on my piece of paper. Okay, it's wrong in my notes, FYI, online, just as an FYI. This is the moment of truth when we figure out what's right in my notes and what's wrong in my notes. I get X of S is 2S minus 3 over S squared minus S plus 6. 2S minus 3 over S squared minus X minus 6. Thumbs up, thumbs down. Are we good with that, with the algebra? Everybody's good? We've got a thumbs up going there? Cool. Okay. Here is the hard part. So let me start a new screen here. And now we're in step 3, which is the hard part. So one more time, step 3, find an inverse Laplace transform. And once again, you have it continued in your notes, but I don't. So 2S minus 3 over S squared minus S minus 6. If you look at the table in the front of your book, you are not going to see that there. It is not going to happen. Does not exist for the table in the front of your book. So what we're going to need to do, and this is going to become a theme all the way through this chapter, is partial fractions. And I'm going to stop sharing my screen for just a minute because I want to pause and restart the video.